Okay, we've talked about the remainder of a series. The remainder R sub n is what's left after the nth partial sum. So previously we've said that the value of R sub n is equal to the value of the series minus the nth partial sum. Well, if our series happens to be an alternating series, this difference might be negative, might be positive. We want to take the absolute value. Okay, the remainder is also the absolute error. Okay, it's the amount of error that we have if we approximate the value of the series with the nth partial sum. We have a theorem in section 8.6 that says that the remainder of an alternating series is always going to be less than or equal to the absolute value of a sub n plus 1. It's going to be less than or equal to the next term after the nth partial sum. The magnitude of the next term after the nth partial sum. So again, not worrying about whether or not it's a positive term or a negative term. The remainder is going to be less than or equal to the first term of the tail. That's another way of thinking about that. Now here's the kind of problem that you're going to be asked to do with that. Suppose we have a series. We're going to start at 0 this time. Don't always assume we're starting at 1. And our series is negative 1 to the k power divided by k factorial. And here's our job. How many terms do we need? In other words, what is the number n to ensure that the error is less than 10 to the minus 4th power? So that would be to make the error less than 10 to the minus 4th power. So again, R sub n less than 10 to the minus 4th power is kind of what we're looking at there. Now here's how I would recommend doing this. We know, okay, here's what I'm thinking. I'm thinking this R sub n is less than the absolute value of the nth or the next term after the nth partial sum. So what I want to do is I want to write out, I'm not going to be able to do it, specifically every single term, but I want to write out, I want to show the first n terms of this series. So if we start at 0, we'll have negative 1 to the 0 power, that's 1, over 0 factorial, that's 1. And that's what we get if n starts at 0. Then the next term is negative 1 to the first power over 1 factorial. And then the next term is negative 1 to the second power over 2 factorial. And then we'd have minus 1 over 3 factorial, and so on and so on and so on. Okay? If we start at n equals 0 and count that as the first term, and then the second term is when n is equal to 1, and the third term is when n is equal to 2, and so on, then the nth term, I haven't quite given myself enough room to write here, the nth term is going to be when n is equal to n. Okay, that's really a bad way of saying this. Let me make some room. The nth term, let's go with k. That's going to fix my problem. So if the first term is when k is equal to 0, the nth term is when k is going to be equal to n minus 1. So we would have negative 1 to the n minus 1 power over n minus 1 factorial. So those terms is the sum S sub n, the nth partial sum. So the next term is going to be a sub n plus 1. And that's where we're going to have k is equal to n. So we'll have negative 1 to the n power over n factorial. Okay, so r sub n is less than or equal to, never mind the negative 1 over n factorial. And that's got to be less than 10, what did I say, to the minus fourth power. So to figure out the value of n we need, we're going to solve the inequality 1 over n factorial less than 1 over 10 to the fourth power. Cross multiply, you'll have n factorial is greater than 10 to the fourth. 10 to the fourth is 10,000. So here we kind of have to start doing some guess and check. Grab your calculator, and I'm going to pause the video while I get my calculator. Alright, got my calculator up. You're going to need your calculator to kind of figure this out. There is a factorial button. No, it's not a button, but the factorial is built into your calculator. 2 factorial, you know, is 2 times 1. And 3 factorial is 3 times 2 times 1. You're not going to have to actually multiply out 3 times 2 times 1 to find 3 factorial. You can key in 3, go to math, over, I use the left arrow once to get to the probability menu, and option 4 gives you factorial. And then you press enter and the calculator does the work for you. So we just kind of want to take a look at the value of some factorials. Oops. Math. 4 factorial, pretty small, so let me jump. 6 factorial. What I've got to do, no, not that. 6 factorial. What I've got to do is find a value of n that's going to make n factorial actually greater than 10,000. 6 factorial, 720. That's not big enough, but they're going to start getting bigger fast. 7 factorial, 5,040. 8 factorial, 40,320. Okay, so because 8 factorial is equal to 40,320, and that is the first factorial of an integer we have that is bigger than 10,000, n equals 8 makes that inequality true. So what that tells us is that we need to approximate the value of the series with 8 terms, the first 8 terms, to make sure that the error is going to stay less than 10 to the minus fourth power. Okay, another thing that you may be asked to do where we're using these same kind of ideas is, let me just get a new piece of paper. Got a sum if k goes from 1 to infinity of negative 1 to the k power divided by 2k plus 1 cubed. Wow, this is what happens when I get in a hurry. 2k plus 1 quantity cubed. Okay, we have a series. We want to estimate the value of this series. With an absolute error less than 10 to the minus third power. Okay, so there are 2 things that we have to do. Number 1, we have to find the value of n that ensures that the absolute error is less than 10 to the minus third power. That's the same thing that we just did in the previous problem. And then the second thing, we evaluate the nth partial sum. Once we figure out what n is, then we can use the calculator if need be to evaluate the partial sum. So, think about the first n terms. Now we're starting our counter at 1, so the first term would be negative 1 over 3 cubed. Let's see, the next term would be positive 1 over 5 cubed. And then we'd have negative 1 over 7 cubed, and so on and so on and so on. The nth term is going to be negative 1 to the n power over 2n plus 1 cubed. So that's our sum, S sub n. So the next term, which would be negative 1 to the n plus 1 power over, now be careful here, 2 times the quantity n plus 1 cubed. That's a sub n plus 1. So our remainder is less than or equal to 1 over, I'm simplifying that denominator now, 2n plus 3 cubed. And we want to know the value of n that makes this less than 10 to the minus third power. So we're looking at the quantity 2n plus 3 cubed greater than 10 cubed. I've done a little bit of algebra kind of mentally there. Now, because n is a positive number, then multiplying or dividing this inequality is not going to cause us to need to reverse that inequality symbol. So I'm going to take a cube root of both sides. Gives you 2n plus 3 is greater than 10. 2n is greater than 7. N is greater than 7/2, which last time I checked was 3.5. So the value of n makes the error less than 10 to the minus third power. So next your job is to find the fourth, we actually know the value of n, the fourth partial sum. Okay, now that's going to be really very straightforward. You don't have to use the formula built in your calculator. I've already written down the first 3 terms, so just add a fourth term to that. Negative 1 over 3 cubed plus 1 over 5 cubed minus 1 over 7 cubed. The next term would be plus 1 over 9 cubed. And if you evaluate that, you get negative 0.030587468. You want to write down as many decimal numbers as you can. So what we're saying is that the series S is approximately equal to negative 0.030587468, and so on.